Hello dear students, welcome to mathematics class. In this class, let us discuss the theorem. If f comma g belongs to R of closed interval AB and f of x is greater than or equal to g of x for all x belongs to the closed interval AB, then we need to prove that integration over a to b f of x dx is greater than or equal to integration over a to b g of x dx. So, in this theorem it is given that the two functions f and g are Riemann integrable functions, and the condition on those two functions is the first function, that is f of x is greater than or equal to g of x for all the x belongs to the closed interval AB, and we need to show that integration over a to b f of x dx is greater than or equal to integration over a to b g of x dx. Now, let us prove this one. Here, since f comma g belongs to R of closed interval AB, so here it is given the two functions f and g are Riemann integrable functions. Then by using this condition we can write that f minus g is also a Riemann integrable function. Since f and g are Riemann integrable, then f minus g is also Riemann integrable function. So, here already we have proved one theorem that if f comma g belongs to R of closed interval AB, then it implies that f plus g belongs to R of closed interval AB. Now, if g is defined as minus g, if g is equal to minus g, then we can say that f minus g belongs to R of closed interval AB. So, therefore, on this basis we have written that f minus g is also Riemann integrable function, and also it is given that f of x is greater than or equal to g of x for all x belongs to the closed interval AB. Here it is the given condition that f of x is greater than or equal to g of x for all the values of x in the interval AB. Then we can write this as f of x minus g of x is greater than or equal to 0 by the inequality f of x greater than g of x, then their difference is always greater than or equal to 0. Then the same expression can be written as f minus g of x is greater than or equal to 0. Now, in the previous class we have defined or we have proved one theorem that is if f of x greater than or equal to 0, then integration over a to b f of x dx is greater than or equal to 0. So, it is the previous theorem. If f of x is greater than 0, then the Riemann integral of that function is also greater than or equal to 0. So, by using this theorem we can write here it is given that f minus g of x is greater than or equal to 0 means f minus g, this together is a single function, that f minus g, that is the difference of two function, means that becomes the unique function, that is f minus g. So, therefore, here f minus g is greater than or equal to 0 means its Riemann integral is always greater than or equal to 0. So, therefore, we can write here integration over a to b f minus g of x dx greater than or equal to 0 by using the theorem f of x greater than or equal to 0, then it implies Riemann integral of f of x dx is greater than or equal to 0. Then this can be written as integration over a to b f of x minus g of x dx is greater than or equal to 0 just by separating the functions. Then here integration over a to b f of x dx minus integration over a to b g of x dx greater than or equal to 0, then this can be written as integration over a to b f of x dx is greater than or equal to integration over a to b g of x dx. So here this is the theorem. In this theorem it is given that f and g are Riemann integrable functions and f of x is always greater than or equal to g of x, then the Riemann integral of the function f is greater than Riemann integral of the function g. The next theorem is, if f belongs to R of closed interval ab and small m comma capital M are the infimum and supremum of the function f in the closed interval ab, then integration over a to b f of x dx is equal to mu into b minus a, where mu belongs to the interval minus m to plus m. So here f is a Riemann integrable function in the interval ab and small m capital M. So it is the infimum and this one is the supremum of the function f in the interval ab. So this much is given and we need to show that Riemann integral of the function f is equal to mu into width of the interval, that b minus a, that is nothing but width of the interval given. The given interval is ab, then its width is given by b minus a, so that is equal to mu times b minus a, where mu is the number which is in the interval supremum to infimum to supremum. So it is the given thing. Let us prove this one. For every partition P of closed interval AB, we have small m into b minus a less than or equal to LPF less than or equal to UPF less than or equal to capital M into b minus a, and consider this as the first equation. So this is the first result on Riemann upper sum and Riemann lower sum that we have already proved in the starting of the Riemann integral. So therefore here m into b minus a is less than the lower Riemann sum is less than upper Riemann sum is less than supremum into b minus a. So this is the important inequality and consider this as the equation 1. Now consider the supremum of all the lower sums. Consider supremum of all the lower sums, where P is the partition of the closed interval AB. Now supremum of all the lower sums is nothing but the lower Riemann integral, that is integration over bar a to b f of x dx. Now here it is given that f is the Riemann integral function. It is given that is f belongs to R of closed interval AB. Since f is the Riemann integrable function, then lower Riemann integral is always equal to upper Riemann integral and is equal to the Riemann integral, that is integration over a to b f of x dx. So here supremum of LPF means that is the lower Riemann integral, that is integration over bar a to b f of x dx, and since f is Riemann integrable function, then we can replace this integral as integration over a to b f of x dx. So here lower Riemann integral is equal to the common Riemann integral, that is integration over a to b f of x dx. Since f is a Riemann integral function, it is given. So here supremum of LPF means, supremum means there is a upper bound of the LPF, and upper bound is always greater than or equal to all the LPF. So therefore, here we can write that each LPF is always less than or equal to integration over a to b f of x dx, and consider this as the second equation. So here supremum of LPF, supremum means that is the upper bound of this set, and this set is nothing but it is a set of all the lower sums. So therefore, each LPF or each lower sum must be less than or equal to integration over a to b f of x dx, because this is the supremum of LPF, and consider this as the second equation. And now consider infimum of all upper sums where p is the partition of the closed interval AB. Now consider the infimum, means that is the lower bound of all the upper sums, and it is equal to upper Riemann integral. By the definition, we can write this one as integration of a to b bar f of x dx, and already we know that f is a Riemann integrable function. So therefore, this integral can be written as integration of a to b f of x dx. Now this is the infimum of all the upper sums. So therefore, infimum means that is the lower bound. So therefore, this becomes the lower bound of all the upper Riemann sums, means this must be less than or equal to all the Riemann sums, because this one is the infimum, means lower bound. So therefore, we can write that integration of a to b f of x dx is less than or equal to each UPF. Since this is the infimum, means least value, so therefore that must be less than or equal to UPF, and consider this as equation number 3. Now from equations 1, 2 and 3, so here it is the equation 1, second equation, and this one is the third equation. Now combining all these three equations, we get m into b minus a less than or equal to LPF, right? And from the second equation, LPF is less than or equal to the Riemann integral, that is less than or equal to integration of a to b f of x dx, and from the third equation, this integral is less than or equal to UPF, so this is less than or equal to UPF, and again from the first equation, UPF is less than or equal to capital M into b minus a. So therefore, here on combining all the three inequalities, we get the result as m into b minus a less than or equal to LPF less than or equal to integration of a to b f of x dx less than or equal to UPF and less than or equal to capital M into b minus a. And the same inequality can be written as m into b minus a less than or equal to integration of a to b f of x dx less than or equal to capital M into b minus a. On the previous inequality, we have written this inequality as m into b minus a less than or equal to integration of a to b f of x dx less than or equal to capital M into b minus a. Now dividing this inequality by the term b minus a, dividing by b minus a, for here the condition must be a should not be equal to b, because if a is equal to b, then b minus a becomes 0, then when we are dividing, that becomes 1 by 0, which is not defined. So therefore a should not be equal to b. Then this inequality becomes m into b minus a divided by b minus a, that becomes m only, less than or equal to 1 divided by b minus a into integration of a to b f of x dx less than or equal to capital M, and here we are dividing by b minus a, therefore we are getting only m. Now 1 by b minus a integration over a to b f of x dx be a number, say mu. Let us consider this as a number mu lying between small m and capital M, that is mu belongs to the interval minus m to plus m. Now we are denoting this total quantity as a number mu. That mu must be lying between small m and capital M, because this quantity is in between capital M and small m. So therefore we are choosing the another number which is lying between the same interval, that is small m to capital M. So therefore we can equate 1 divided by b minus a into integration over a to b f of x dx is equal to mu, because this is equal to the mu that we have considered, because this quantity is also in the same interval and mu is also in the same interval. So that is why we are denoting this total quantity as mu. Then it becomes integration over a to b f of x dx is equal to mu into b minus a, which is the required proof of the theorem. So in this theorem it is given that f is a Riemann integrable function and small m and capital M are the infimum and supremum of the function f. Then we need to prove that integration over a to b f of x dx equal to mu into b minus a, where mu is a number in the interval small m to capital M.